All right, hello everyone, welcome to episode 53 of Warsaw Quantum Computing Group Meetup. My name is Paweł and I will be the host today. And today we have a pleasure to have a great speaker from the University of Warsaw, Professor Magdalena Stobinska. She will give a talk about quantum communications. Before we start, I would like to thank our strategic partners for supporting us, Cogit, Narto, and Sonovero R&D, and our honorary partners for also helping us in advertising these events and organizing everything smoothly. With this, I will stop sharing. Before we start, maybe just one more announcement regarding questions. You are welcome to ask questions during the lecture, but in order to just make sure that everything is fine and smooth, please raise your hand if you have a question, or you can also write your question on the chat. So there will be also a Q&A session at the end after the talk. If there are some urgent questions directly related to the slides, we'll try to interrupt and just answer them straight away. But if there are some more general questions, maybe we'll just keep them for the Q&A session at the end. Okay, I think we can start. So Magdalena, thank you very much for accepting our invitation. We are looking forward to your talk. If you are ready, you can start sharing your slides and.
Yes, thank you very much for the invitation. It's a great pleasure. If anyone has questions, please let me know. I may not notice your hand recent, so then just feel free to interrupt me. Okay, can you see my slides?
Yes, I can see your slides.
All right. Okay. Okay. So I guess I can start. Right. Okay. So welcome to the brief overview of quantum communications. Quantum communications is worth investigating because it's one of the key quantum technologies that is actually closest to commercialization. It's the most developed of all the technologies. It has very well defined the benefit that it offers with respect to the classical technology that it could complement. So I would like to guide you through the concepts, through the protocols, the newest implementations, achievements, field tests, and to show you the prospects and the future directions in which probably this field will develop. So this is the brief agenda of my talk. I think I'm having the presenter's view, right? Are you sure?
Yes, we can see the presenter view now.
That's
okay, now we can see it.
I'm very sorry. Now it's somehow okay. Now can you see it well? Okay.
Yes.
All right. So let me start with the motivation, so we can understand why this effort. Why at all are we seeking for? We are leaving our comfort zone and we are seeking for new cryptographic solutions. Let us then recap and quickly understand what is the difference between quantum and conventional communications. Then we will acquaint ourselves with the zoology of quantum cryptography protocols, because I have noticed that there is a tendency in general for non-experts to perceive quantum communications as just one solution, which is not true. There is the whole zoology and they offer different benefits So it is important to be acquainted with all the options and understand what these options offer and what these options do not offer. This is very, very important, as cryptography is about the security, and unfortunately, the more secure solution is, the more difficult to implement and the more expensive it is. So if somebody would like to somehow optimize, it's important to understand at what cost. Then I would like to acquaint you with quantum implementations of various protocols. I will briefly mention what post-quantum cryptography is, as post-quantum cryptography is also often confused with quantum solutions. It has nothing to do with quantum, despite its name, but it can nicely complement the quantum cryptography. Then I will talk about hybrid solutions that merge quantum cryptography and post-quantum cryptography. And I will briefly summarize the standardization efforts that are very, very strong in the community at the moment. And these activities take place worldwide, not only in European Union. Okay, so here is the problem that we have. Imagine there are two people, some Alice and some Bob. It can be you and me. And they want to actually communicate securely using, for example, the internet. This internet symbolizes here an open public channel. It can be internet, it can be your phone, just, you know, any public medium. So for the moment, they want to communicate securely, but this channel might be actually intercepted or tampered by some third party here called Eve. And to prevent that, Alice encrypts the message with a cryptographic key, which is known only to her and Bob, and sends over the channel the information. When Bob receives it, he decrypts the message with the same key. And the key should be used only once. And that could provide us with great security. But how to securely exchange the cryptographic keys without meeting in person? That's a great question. Because now if you think that everyone with everyone in the world, so for example, I don't know, for example, you can be a client of a bank in New York and you have to exchange the key with the bank in New York, and the bank in New York has many clients, that would require everybody going there physically to exchange the key. Of course, this is not possible. Therefore, we are seeking some remote way of exchanging keys. That is the conventional solution with which we are dealing now. So what's being done is we exchange the keys using so-called public key infrastructure, which amounts to that Bob announces his public key to the world, and then Alice can download it and encrypt her message with it. Then she sends the message over the channel, and Bob can decrypt the message with his private key, known only to him, and that is supposed to cover the communications between two parties. The problem is that public key infrastructure is based on Rivest-Shamir-Adleman algorithm, which assumes hardness of prime number factorization. However, there is inside the implementation of quantum Shor's algorithm for which shows that prime factorization that was very difficult for a classical computer becomes very fast on a quantum computer, and therefore breaking public key infrastructure becomes easy. So this puts us in an awkward position that the solution that we found to the problem of exchange keys actually lowers the security of communications. So the benefit of easing the key exchange was done at the cost of lowering the security of communications. One can say, yeah, but you know, quantum algorithm, quantum computer is far away from our real life. It's not existing yet. So do we really have to worry about this problem? Do we really have to wait for this quantum computer? And the answer is no, we don't. So it turns out that crime that relies on breaking the public key infrastructure became an industry. And here I'm showing you just an exempt from the exemplary GitHub account called VX Underground, which actually offers 36 million of malware that is designed for breaking the public key infrastructure. So, of course, these kind of programs, these kind of hacker groups are exactly focusing and specifying themselves at breaking the encryption that is used now. And this has already concrete numbers that you can see on this graph, showing the number of data compromises and individuals impacted, the number of records exposed in millions. This is the black line, the data compromises blue line, and the individuals impacted in millions. So as you can see, the number of incidents grows in years, and the cost of these incidents grows in years. So as you can see, we do not have to really wait for the advent of the quantum computer to conclude that there is something to be done about the current encryption schemes. So this is just a graph, but this should show you, this is supposed to be a movie that should show you how this goes in real time. Can you see the movie or not really?
I can see it.
It's do you see the film?
Mm-hmm.
Yes. Oh, perfect.
Yes.
Sorry, because on my computer it's completely static. Can you see?
Yes.
So this map shows the real-time attacks that are actually now occurring in the world. Is the demo? Oh, now you can see how many cyber attacks are occurring at this moment in the world. So, for example, it's quite easy to spot where the Brussels is. Now we see the US. Soon we will see Europe. And as you can see, United States, the second most attacked country. So this gives you the statistics of various kinds of attacks that are occurring in this moment in the world. Okay, so what is the quantum versus conventional communications? What is actually the difference between quantum and conventional communications? So if we say we are communicating, what is actually happening? So first, if we are communicating with someone else, we have to verify, perform channel authentication and verify whether this person is really who we think he is. Then we have to encrypt our message and send it over the medium. And then we have to verify whether sending was fidel. Quantum communications takes place in a very similar way. However, some of these steps are implemented with quantum resources. Quantum communications assumes classical channel authentication and then distribution of quantum resources, for example, qubits or entangled states, and then quantum encryption. So as you can see, quantum communication, in fact, by design, requires hybrid solutions. So the question to you, do you trust math or physics? What is the difference between the conventional encryption and the quantum encryption? So in a nutshell, how to recognize it very quickly? Conventional encryption is based on algorithms. And therefore, the level of security that it offers is based on assumptions of computational hardness of certain problems. Therefore, it is called computational security. This is security that breaks at certain threshold of the computational power of our adversary. The encryption that is in use now, as well as the post-quantum cryptography solutions, belong to this class. Quantum cryptography, on the other hand, is free from algorithms. It is not based on any algorithm. And the security that it offers is based on the laws of quantum physics. The encryption is based on quantum superposition, on quantum entanglement, and therefore on genuine randomness. So here comes a question: for how long am I conventionally secure? The truth answer is nobody knows. As public key infrastructure is based on computationally hard problems such as integer factorization, discrete logarithm problems, elliptic curves that are hard for conventional computers, we might think we're pretty safe. However, there are some data that may worry us. For example, already many years ago, in 2012, a quantum computer factored number 21, and in 2019, number, oh my God, I even don't know how to read it. It's a 3, 6, 9, 12. It's a 10 to 12, as a number as large as 10 to 12 was factored by Zapata Quantum Platform. In 2016, NIST announced that a quantum computer is likely to be built by 2030 that breaks 2000-bit RSA in a few hours. In 2020, factoring of 829-bit RSA with HPC was announced. HPC, high performance computing. So as you can see, no quantum power here. In 2023, Chinese announced that 372 qubits are enough to break a 248-bit RSA, which is currently recommended for e-commerce encryption. For this reason, every few years, NSA issues new recommendations for key length. And the answer is for 6 hours, maybe I'm safe. As you can see from the press releases, conventional security may break very suddenly. Interestingly, in July 5 last year, NIST has announced that they are close to finalize their PQC standardization process. They have announced 4 candidates to be standardized, plus 4 auxiliary candidates. One of these favored candidates has been developed since 2011 by IBM and is called the Supersingular Isogeny Diffie-Hellman protocol. 1 month later, after this public release by NIST, this protocol was actually broken in 6 hours on a laptop. It was because someone Googled up an old mathematical paper with a theorem in it, which helped to break the protocol. Later, the program for cracking it was optimized to crack the encryption in 30 minutes. So that was quite unexpected course of actions. Okay, so this kind of surprises makes us always think, okay, but actually let us recall again, what makes us quantum secure? Are we overlooking maybe something? So let's examine again, what are the assumptions behind quantum security? So there are 4 here listed. First of them is that quantum theory is correct. So for example, quantum information cannot be copied because no cloning theorem applies. The other is that quantum theory is complete. That is, there are no extensions that will give the attacker any additional information about our protocol, about our devices that implement it, about the carriers of the information. Another, very important, is that free randomness exists so that Alice and Bob can choose their settings in a truly random way. So we do have to have access to genuine randomness. So no pseudo-random number generators. We have to have genuine randomness generator to implement quantum security. And fourth, although these 3 that are seem to be pretty abstract, and I wouldn't say that they are very worrying. Instead, they are very, I'm quite relaxed that they are fulfilled, as quantum theory is the most tested theory in the laboratory. There is a 4th one, which is of concern. That is, our quantum cryptography has to be implemented correctly. What does this mean? Every protocol has certain assumptions with regard to the specifics of the devices that implement them. For example, that our sources of entangled particles produce specific state and they do not produce any other state. Or, for example, that our measuring devices perform this kind of measurement and not something else. This kind of specifics with regard to the hardware may open the security loophole if the assumptions of the protocol are not met in practice. And this is actually a frequent cause of hacking quantum protocols. So this 4th one is the most important one, actually. Quick summary of quantum versus conventional encryption. So quantum cryptography is based on the laws of physics, and it can offer information theoretical security, which means it can offer solutions that will be resilient to all known and yet unknown cyber attacks. However, it will not replicate all the functionalities that we have now with public key infrastructure, and it will be costly because it requires building a whole new infrastructure that is quantum network. Instead, post-quantum cryptography, it's easy to implement because this is software-based security. It's based on algorithms, for example, code-based cryptography or lattice-based cryptography. I'll show you later. And it's compatible, immediately compatible with the public key infrastructure schemes. It offers high key rates. However, it offers only computational security, and it's resistant only to currently known attacks. Namely, post-quantum cryptography is all classical algorithms that are resistant against Shor's algorithm. So everything that is beyond the discrete logarithm, prime number factorization, elliptic curves can be understood as post-quantum cryptography. Okay, so we know pros and cons. These are two complementary approaches. Therefore, maybe we can actually build a solution that is harnessing both approaches and actually creates a new added value based on the synergy between them. That would be called a hybrid solution, and this is the current trend. So what a hybrid communication would be, that would be authentication of channel using post-quantum cryptography algorithm that will for sure equip us with short-term security, which is completely enough for the activity of channel authentication and user authorization, so verifying access rights. This activity is very short in time, so the likelihood that somebody will break the algorithm in this short time is very small. And if it will break the algorithm after we finish these procedures, it will not hurt us at all. Then hybrid communication is based on distribution of quantum resources and quantum encryption. That is quantum key distribution, which will provide us with long-term data encryption, which prevents from retrospective decryption. So download now and decrypt later. Okay, so I guess having this brief overview and understanding what are the pros and what are the cons between the two approaches, we can now more closely have a look at the quantum cryptography protocols. What are these solutions and what they can offer? So I think we can distinguish 4 different classes of QKD protocols that are shown on this pyramid. And only one of these classes actually offers unconditional security that can be verified in real time. That is called device-independent QKD, and I will talk about it in a second. All the other protocols either do not have the means of verification of the security. These are the entanglement-based QKD protocols, or have been shown to be hackable. The most popular class explored now is the prepare and measure QKD. Here comes the very, very known BB84 protocol. The other class is semi-device independent quantum key distribution, which often boils down to the measurement device independent protocols, where some of the assumptions with regard to the inner workings of the devices that implement the protocols are lifted. Namely, we can trust the measurements that are carried out. And these two classes have awaited implementation and test fields. Although they are very interesting from the academic point of view, they have been shown to be hackable because their implementation does not correspond to the assumptions that stand behind the protocols. Another class, entanglement-based QKD protocols, have the potential of unconditional security, but we do not have the tools for performing the verification that indeed no one was wiretapping our connection. Only the device-independent QKD protocols have that option. They are also entanglement-based. However, they are supplemented with a quantum statistical test, the Bell inequality test, that checks in a real time the security of connection. So while extracting the cryptographic key, the users can also control if someone is trying to tamper or wiretap their connection. So Having said that, let me show you this is absolutely just an exempt from all possible protocols that exist. There is a really vast number of them, but here I am just enumerating several. Maybe some of you have already seen them and read about them. I would like to focus maybe on selected ones, these which are highlighted in red. So prepare and measure protocol, that would be BB84. For measurement device independent, that would be Toshiba Twinfield protocol. And for entanglement base, that would be E91, Eckert 91. And I would like to talk about two device-independent QKD protocols. The one which is based on the E91 protocol plus CH-SH Bell inequality test, and a protocol that we have worked out here with my collaborators in Warsaw, which merges two qualities. That is device independentness and long range distribution. So let me start maybe with the BB84 protocol. This is the seminal protocol created by Bennett and Brassard in '84 that has actually opened our eyes to how we can actually use quantum superposition and quantum entanglement for extracting genuine randomness and cryptographic key. This is a protocol that actually also help us understand how quantum information can be shared. That if it's wiretapped, we see it as a disturbance. So we can actually understand quantum information as a quantum resource. So let us start at the beginning. There is Alice and Bob, and Alice wants to send Bob some information. To this end, she's creating randomly single photons in one of the four polarization states. So as you can imagine, each of these polarization states acts like as a qubit. So we have two qubits. Every qubit has two possible classical bits that it encodes actually. And she's creating these qubits prepared in different superpositions. So preparing, for example, qubits in horizontal and linear polarization, which is actually shown by the arrows. So arrows which are horizontal and vertical correspond to linear polarization, and the arrows which are skewed correspond to circular polarization. She's randomly preparing these qubits and sends over the optical channel. These qubits arrive to Bob, and Bob is taking measurements in randomly chosen bases. So he does not know what sort of qubit Alice has prepared, and he is randomly choosing the basis of polarization in which he will measure. So this will be either horizontal or circular, which correspond to measuring sigma X or sigma Z operators. As a result of this, he receives a binary output, which is here shown as 1 and 0. And this experiment takes some time until actually they will collect some statistics, after which Alice and Bob publicly announce their choices of bases. So Alice communicates subsequent choices of horizontal and circular bases in which the qubits were prepared, and Bob does the same, that is, he announces the circular or horizontal bases in which the qubits were measured. In case there is no agreement with respect to the basis. So for example, Alice prepared in horizontal, in linear polarization, and Bob has measured in circular, they discard this data. Therefore, in the end, they will lose some data from the statistics, but they instead will create so-called sifted key. So the key which reveals perfect correlation between the two parties. Next, they have to verify the security of this key. The key is already correct, but is it secure? For this reason, Alice and Bob will compare random samples of their sifted key bits and will compute the error, so-called quantum bit error rate, QBER. And if this QBER will be too high, they will conclude that there was some attempt of interception, and therefore they will abort and repeat the whole procedure from the very beginning. Otherwise, they will accept the key, which can be used for encryption of the message. It is very important to notice here that Alice sends these qubits via open channel. So these qubits are sent without any amplification, without any storage. They are directly sent to Bob. Okay, so this is what happens in the perfect situation, but life is not perfect. And what if there is somebody who wants to listen their communication, some Eve? What if she attacks the quantum channel? So in the simplest situation, what she can do is she can perform the intercept resend attack. So what is happening here? She's cutting the quantum channel. She's catching the qubits which are prepared by Alice and measuring them, learns the information, and resends prepared qubits accordingly to this measurement outcomes to Bob, who doesn't know what is happening and performs his measurements as if everything was without any problem. Are Alice and Bob able to learn that Eve is in the middle of them? Yes, they will be able to do that, thanks to the quantum property that information gain is seen as the disturbance of the statistics that Alice and Bob collect. So to see how they will learn, let us focus on cases that Alice and Bob will use the same basis, and they are throwing away all the cases where the bases are not the same. Eve can guess correctly the basis only 50% of times. Therefore, her attack will introduce 50% of errors for half of the total bits. So for the whole statistics, she will introduce error of 25%. So let me repeat again. We are just focusing on the situation where Alice and Bob have agreed for the basis, which is half of the times roughly. But Eve doesn't know the answers. Eve has to guess again completely independently from Bob. So half of the times, in this half of the times that they are agreed, she will make a mistake. This amounts to 25% of QBER. So when Alice and Bob will sacrifice some of their sifted key and compute the QBER, and it will be as high as 25%, they will immediately discover that somebody was listening. And this is a very important conclusion from this simple protocol, very academic, but very important because it teaches us that quantum information should be seen as a quantum resource. Quantum information, quantum measurements allow us to quantify very precisely the amount of information that has been sent from Alice to Bob and the amount of information that has leaked from the channel that actually links them. So this is the property that we do not see within classical communications. If we are, for example, talking over phone and somebody is wiretapping the line, we do not observe any deteriorated communication. It's not that we are receiving erroneous information instead. So this is the very feature of the quantum world, that we can quantify how much of information, and notice how much of information has actually leaked. Okay, so BB84 is the seminal protocol that exemplifies how prepare and measure protocols works. So Alice prepares the qubits, sends over to Bob, and Bob measures. They are comparing the statistics, establish the key, quantify the error, and judge whether something has happened or they were communicating securely. Can this protocol be actually secure? It can be probably secure, relying on two conditions: that the information quantum property, that information gain is only possible at the expense of disturbing the signal if someone is listening, and the existence of an authenticated public classical channel through which Alice and Bob communicate. There is another assumption, as I have already mentioned, that we have implemented this protocol correctly. That is, all the devices used, so the source, the measurements, actually carry out the operation as designed. This, unfortunately, often is not the case in real life. Okay, since these protocols I have already mentioned, let me repeat again. I gave this remark that it's important to notice that Alice sends to Bob the qubits as is, without any amplification, because, as you know, quantum information cannot be amplified, cannot be copied. Amplification always somehow amounts to copying, so we cannot amplify quantum signals. So a practical question comes to our mind: okay, when she's sending these qubits like this in open air or through fibers or whatever, how far they can actually get before we will lose them, right? This open channel is a lossy channel. Usually there is a lot of, processes, I don't know, dissipation or phase, the polarizing channel, or simply other disturbances such as varying temperature of the fiber or atmospheric condition, all kinds of factors that alter the states and wash away quantum properties they carry. So how far they can communicate? So the present implementation show that it's the distances of about 100 kilometers, 100, 120, depending on all these factors, depending whether we will use ultra low loss fibers or fibers that are in use for communications now, but it's about of 120 kilometers. So the distance is not really impressive. And can we break it? Can we actually develop quantum communications beyond 100 kilometers? And Twin Field Protocol has shown that, yes, it's possible. We can actually develop quantum communications to larger distances. And the protocol was developed by Toshiba, where they have shown how to achieve the distance, which is at least doubled. So in this arrangement, we are not dealing with prepare and measure protocol. It's not that Alice prepares the qubits and sends to Bob. Alice and Bob here are both senders. This is protocol that belongs to measurement device independent class. So what is happening? Alice and Bob prepare phase randomized optical fields that are generated and then sent to a central measuring station. These fields are imparted with some random phase, phi1 and phi2 on this presentation, and the choice of them is completely random. And if they are equal, so if phi1 equals phi2 by chance, these two optical fields can be called twins and can be used to distill a quantum key. This is a measurement device independent protocol because the central measuring station, Charlie, must be trusted. This is the first protocol that allowed us to break this 100-kilometer limit. So what happens? These pictures show the real implementation of the protocol. Alice and Bob produce some coherent states. These coherent states are equipped with a random phase, rho A and rho B. On the graph, it's shown delta A, delta B, because it already includes some noise, some imperfections that occurred in addition to the random phase choice. And these pulses are sent for interference at the Charlie station. It's important to notice that the choice of the phase is taken random with a uniform distribution from the interval between 0 and 2 pi. Of course, to somehow make the process of selection of phases that sometimes will match more efficient, this interval has been chopped into slices, which are shown on the right. The number of phase slices has to be chosen carefully in order to minimize an intrinsic qubit error rate in this protocol that arises from the fact that even if rho A and rho B are chosen from the same phase slice, they may not be actually equal to each other. So the number of slices is optimized with respect to this internal error called intrinsic qubit error rate. And the number of slices which cannot be too high, because in this situation, the occurrence of equal phases would be extremely a rare event. So these two coherent pulses are sent for interference at Charlie, and Charlie is supposed to detect a single click in one of his detectors. So the two fields that are observed by Charlie are also coherent states. If the two phases are equal, sometimes if the two phases are equal, one of the detectors will not click. And these are the occurrences for which Charlie is actually waiting. So sometimes one of the detectors does not click, the phases are the same, and in this way, they can extract the information from the phase, which is carrying the global information in this scheme. An important feature of this doubling the distance at which the quantum communication can be expanded here can be understood on these figures, which show that, in fact, twin field protocol is based on a single photon interference that occurs at Charlie. So the upper and the middle row in this graph demonstrate the usual QKD protocols with phase encoding. So the two photons are traveling the distance of L between Alice and Bob, and they both are subject to losses. Instead, in the twin field protocol, when Alice and Bob are both senders, the photon, in case of a single photon event observed by Charlie, only one photon could reach from Bob to Charlie or from Alice to Charlie, and therefore only one photon was subject to loss. As you can see in this twin field protocol, in this bottom row, in this twin field protocol implementation, the distance between Alice and Bob is doubled. So this actually is, for a given count rate, helps us to double the distance of the reach of quantum key distribution. Thanks to that property, the protocol gains square root dependence on the key rate for the channel transmittance, as you can see from this graph. So the ideal twin field protocol is shown with the dashed line, the linear dashed line. The implementation is shown with the solid black line. Of course, because of losses, we have some finite reach, but an important region to spot here is the most red one, where the twin field protocol overperforms protocols that are corresponding to the best prepare and measure or measurement device independent protocols that are denoted by 1, 2, 3, 4 lines, solid lines that are corresponding, for example, to BB84 protocol. So this region that is the most red is the gain, is the benefit of using this particular implementation, and help us significantly increase the key rate for a given distance. As I have mentioned, all these protocols that we were talking about are very interesting from the point of view of studying quantum information. But if we're thinking about implementation, we have to always make sure that the assumptions that stand behind the protocol correspond to the actual performance of the devices that implement them. And unfortunately, this is not always the case. And here you can see the list, which is taken from Reviews of Modern Physics, published in 2020, where there are listed successful attacks that were performed on both types of protocols. And they not only show the year when this attack was performed, but also the part of the setup that was hacked. So, for example, for the first one, that was the source, for the second one, detection, and so on and so forth. So this is extremely remember if we're implementing the protocol to make sure that your device is doing what it's supposed to do. However, there will be never certainty, and the question, it's an open question, how to test devices that make up the cryptographic setup so that we are absolutely sure that they are not having any flaws. For this reason, we are slowly shifting towards entanglement-based protocols that are important because they will subsequently free us from these needs. So quick recap, what is entanglement? Entanglement can be understood as correlated randomness. So here we see the typical most simple entangled state called the singlet state, which is a bipartite entangled state between some A and B. And the feature of that state is whenever party A measures a photon in polarization that is horizontal, H, the corresponding party, without taking any measurement, with certainty will know that their photon is in an orthogonal polarization V. So this acts like dyes that are correlated with each other at a distance without any limit, without any limitation to the distance. So each time that the two dyes between one at the premises of Alice and the second at the premises of Bob, for example, Alice is in London, Bob is in New York, each time these dyes are thrown, the output of these dyes is completely random. Each time they obtain a different number, but always these numbers will be the same despite the distance between them. And this exactly is the source of randomness and the tool for verifying that the correlation is there. Okay, so the first protocol that was entanglement based was designed by Arthur Eckert in 1991. And there, Alice and Bob they share a singlet state, for example, photonic singlet state, that is distributed by a source of entangled pairs that is put in the middle between them. And as you already know, each time when they take measurements, they see a random output. Alice and Bob, can actually choose two different measurement settings, which I denote here A1, A2, B1, B2, that will correspond to the measurement of sigma X or sigma Z basis. The decision which setting they will apply and then perform measurement is completely random. This was one of the important assumptions behind the security of QKD. Next, Alice and Bob publicly announced the observables they measured, but they never revealed the measurement outcomes they obtained. So plus and minus 1. For these cases, which is about half, in which they measured different observables, they discard outcomes, as they are not correlated. It's like in the BB84 when they had no agreement between the bases they were discarding. For these cases where they agree on the same observable, their results, although they are completely random, are perfectly correlated, as I have just explained on the example with dyes. And in this way, they are establishing a random key. This is a very interesting protocol that gave birth to another completely class of protocols. The class of protocols that is called device-independent quantum key distribution. So the basic setup is the same, however, it is supplemented by Bell inequality testing. So the statistics that is gathered by Alice and Bob in this binary measurement outcomes is also tested for Bell inequality. In a device-independent protocol, there is also one additional setting, either on the part of Alice or on the part of Bob, which is used to extract the cryptographic key. So by taking choices between B1, B2, and B0, Bob can switch whether, together with Alice, they are testing for secrecy of the key or they are generating the key. Important concept in this protocol is the fact that the secrecy and security of the key is based solely on testing quantum correlations. Once they will perform the Bell test and they will demonstrate Bell inequality violation, they do not have to inquire what are the inner workings of the devices, of what are the specifics of the implementation of the source of entangled pairs, how their measurement devices work, whether they are trusted or not trusted. They can be even at the hands of the eavesdropper. They don't care. They only care about the fact that in these circumstances, whatever they are, they were able to demonstrate violation of Bell inequality test, and then they could extract a key rate that is non-zero. The simplest implementation of the Bell inequality test is the CHSH Bell inequality, where Alice and Bob use their settings A1, A2, B1, B2, and measure, for example, sigma X, sigma Z Pauli operators. And sometimes they switch, that is testing for the secrecy, and sometimes Bob switches to the third setting, B0, which allows Alice and Bob to compute the so-called Devetak-Winter formula that quantifies how much of information has leaked to Eve, how much of information they have lost in order to correct for the errors that were established in the protocol when incompatible measurements were chosen. This key rate, if it's positive, it proves the fact that this protocol has been carried out without any disturbances. As you can see, the key rate is solely quantified by the value of the Bell parameter that they have obtained. And this fact, this concept that testing quantum correlations can provide us with some lower bounds for security and positive key rate, is the heart of the device-independent QKD. This kind of concept can be further generalized, and together with my group, we have worked out a device-independent protocol that has the feature of twin field protocol, which allows to reach larger distances. This is the distinguished feature of this protocol is the fact that it's implemented with existing hardware. There are no assumptions behind. It is using the hardware that is available in optical photonic laboratories, such as spontaneous parametric down conversion and single photon superconducting nanowires to measure and perform the Bell test. Interestingly, it is super robust with respect to losses. And if we now look at the graph, especially the upper dashed black and dashed green line, we will see that they are superimposed while they are corresponding, the black one to the ideal conditions and the green one to the 40 dB losses that occur on the way between Alice, Charlie, and Bob to Charlie. So this protocol can be carried out, can provide you with a device-independent long-range quantum key distribution, even in the presence of losses as high as 40 dBs per link between Alice and the central station. This is a remarkable feature that renders this protocol useful for satellite communications. Maybe I will proceed with a little bit, because I see that we are slowly running out of time. I would like to show you the quantum implementations. So the state-of-art prepare and measure system has been obtained by ID Quantique. That was first Swiss, now it's South Korean company. The record of 421 kilometers was achieved in 2018 with 2.5 gigahertz source and superconducting nanowire detectors inside. And they have achieved the key rate of 6.5 bits per second. With respect to the twin field systems, Toshiba has implemented its protocol for a fiber as long as 240 kilometers, and subsequently in 21 for 555 and 600 kilometer link. The key rates they have achieved was 300 kilobits per second for the 120 kilometers, up to 0.7 for beats per second for the longest fiber. So you can see how the key rate actually drops when it's sent over the fiber. So the issue of distance, of designing the protocols that allow us reaching distances as long as possible by design is super important from practical point of view. So records in fiber-based QKD belong to China. They have already developed the whole network. For example, 2 metropolitan networks with ultra-low loss fibers, and they performed twin-field QKD for a link of 511 kilometers. In 2022, that was extended to 600, about 660, and 800 kilometers later on. The key rates that they have achieved sometimes are very low. For example, for a link of 2,000 kilometer fiber, the key rate was 0.003. For the 500 kilometer link, that was about 3 bits per second. Nevertheless, they are putting a lot of effort in developing this technology, not only in fibers, but also in space. The space implementation seems to be slightly counterintuitive because, of course, this adds another layer of problems, because not only quantum, but also in space, putting all this equipment, which is fragile, needs to be cooled on the satellite. Well, it does not sound appealing. But in fact, from the quantum standpoint, it makes a lot of sense because it reduces the losses. As you can see in the fibers, the key rate drops significantly very fast. And with the space links, so link between some ground station and satellite, or satellite and ground station, so depending downlink or uplink, we can minimize the losses because they occur only in the atmosphere, and atmosphere is about 20 kilometers thick. That means that if we are, for example, trying to communicate from London to New York, which is a distance about 5,000 kilometers with a fiber, that is no-go. But with a satellite, we are facing 40 kilometer losses. So one time we have to pass atmosphere up and one time down. So that means with this implementation, it's from the losses point of view, New York is 40 kilometers away from London. So these are the MISHUS satellites missions that are pursued by China since 2016. And in 2021, it became a part of a almost 4,500 long quantum Chinese network that involves free space and fiber networks. These implementations focus on entanglement-based QKD, BBM92, which is a very similar protocol to Eckert's protocol. Not only China is pursuing space missions, there is also Singapore, Canada, the US. There are European missions. There is Japanese mission. Nevertheless, China is definitely the leader here with its MISHUS satellites and Jinan that was launched last year. MISHUS 2 is going to be launched in the next year. So this is the worldwide map of the QKD satellite missions that are ongoing or planned and will soon take the place. Okay, so post-quantum cryptography, also in a nutshell, post-quantum cryptography, as I have already mentioned, has nothing to do with quantum mechanics. It is based on problems that are believed to be computationally hard and for the moment are resistant to the Shor's algorithm. Therefore, PQC cannot offer unconditional security, but only computational security. The advantage of this solution, very much supported by National Institute of Science and Technology in the US, NIST, is the fact that PQC is a software solution and therefore integrates well with the existing ITC infrastructure without any significant hardware cost. So in a nutshell, what are the problems that are considered to be hard that are harnessed by PQC? There are many kinds of them. I think I will just mention two of them today. There is one type of PQC that is called lattice-based cryptography. We are then considering a periodic grid. And within this grid, which is supposed to be not only two-dimensional, but multi-dimensional, many-dimensional, for example, we have to find or detect the shortest non-zero lattice vector to our chosen vector. It appears that this problem requires exponential time and space, even in the quantum implementation. This is known as the short integer solution problem, and it gives rise to one-way functions, identification schemes, and digital signatures. So a little bit of details. If we will imagine n-dimensional integer vectors that are computed modulo some number q, we can formulate a problem that we are searching for a non-trivial short vector that is somehow which length is upper bounded by some coefficient. And it should provide, it should become a kernel of some uniformly random matrix. And the constraint that the length of the vectors is somehow upper bounded, it has to be, it is not taking the full span between 0 and q, but instead it's upper bounded, but some beta, which is small, renders this problem very hard. And to see why this problem is actually useful for cryptography, we can consider collision-resistant hash function for which we will define compressing from the grid, from the set of m-dimensional sequence to this grid. We want to compute the action of this uniform random matrix on certain input from the m-dimensional sequence. And now collision, that is the x for which the function will x prime, for which the function will take exactly the same value, will searching for this x prime that for which the function will take the same value can be bring down to finding the short solution. So this will be exactly the problem of finding short solution problem z, which is the difference between the two values. So you can see that based on a hard problem, trying to find a vector that provides the kernel of a matrix can be reformulated in terms of a collision problem. So we cannot find another input for such a compressing function that will give us the same answer. Another type of problems that are used is so-called learning with errors. Here we are also on a multi-dimensional grid, and we are trying to guess some function or given some number of samples, but these samples are affected by errors. This problem is conjectured to be hard, and the best known classical algorithms need exponential number of operations to tackle it. And these problems are used to generate public key encryption and identity-based encryption. So how does this problem look? Let us consider again grid that is n-dimensional, and the vectors in this grid are at most q long. And we are searching for, we want to investigate some noisy inner product. So we have two vectors, A1, B1, A2, B2, but this B1 is actually the effect of some noisy inner product between A1 and secret vector S that is affected by error E1. So once we have these noisy inner products and we would like to identify this secret key, we would have to solve an equation that is shown as a matrix formulation below. And this error, the presence of the error in this equation, the vector E, makes this problem hard. Otherwise, we would be able to find inversion of A very quickly. So these are the two types of, only two types of problems that are harnessed by post-quantum key post-quantum cryptography. However, there are many other problems that are used. I would like to tell you that now the current trend in the field is to merge and use public post-quantum cryptography for authentication of the channel between Alice and Bob, and then performing quantum key distribution towards offering a solution that is integrable with the existing infrastructure and providing the ultimate security for the encryption of data. And the first protocol, the first hybrid cryptography protocol has already been demonstrated by the Chinese group of Jianwei Pan 2 years ago. It was based on the BB84 type of protocol that was amended by an algorithm, IDC, post-quantum cryptography algorithm, based on lattice problems for authentication in the public key infrastructure scheme. The additional benefit, into leveraging the security of this communication was reducing the connectivity load that for end users in typical QKD protocol scales as O of n squared to linear connectivity. This allowed exploring the networks without the necessity of every two partners in the network exchange the security keys before the communications. In experiment, the application of PQC in QKD point-to-point link was realized with fiber distances between 10 and 100 kilometers. So in this solution, Alice and Bob share quantum channel where they carry out a QKD protocol, here BB84, but they also share a classical channel that is encrypted with PQC that is used to the generation of public keys and private keys for encryption of the messages and decryption of messages for the authentication of the channel only. So
Maybe ask a question, because it seems there are two questions now, or even three questions related to the previous slide. So I think that Michał was first. Michał, can you maybe unmute yourself and ask your question? If it's fine for you, of course, because yes.
Would that make sense to work opposite way? So first exchange key with QKD, because it seems QKD is very inefficient way of communicating encrypted text if you want to communicate megabytes or gigabytes of data, and then use PQC with the key that was secured with QKD, because you told the opposite way.
Yes, but maybe it can be done in steps, but we first have to remember that every QKD protocol assumes existence of authenticated channel between Alice and Bob. Because if we want to exchange the keys in quantum way between two people, they have to be sure that they are who they are, that they are not exchanging the keys with an adversary. So the step of authentication needs to be carried out first.
Right, but most authentication, to my understanding, at least in cryptography, relies on the presence of the encrypted channel or a means of encryption. So we can, in theory, we can first exchange the keys and then confirm that the person who has the key is the right person. Or would that break for some reason, like mathematical reason?
I'm afraid that in this way, how can you exclude the adversary? I don't know.
So we exclude adversary by the second step. So most non-quantum cryptographic protocols have multiple steps. First is not necessary authorization, right? The first is to establish the connection itself.
So I think that in QKD protocols, you need to first authorize. You need to first authenticate and authorize that you are exchanging the key with the person you want, because otherwise this could have been an adversary and it will verify itself with certainty, right?
Well, if it's exchange with adversary, we have a new unique key, because the problem of establishing new key is standard, right? So we have a new key exchange with one person, as long as it's not the same as the key exchange with somebody else. If it's fresh key, that should be all right. Or is it always the same key that each partner in the encryption algorithm uses?
No. You always use a separate key. You generate separate key. With
so mathematically speaking, if we have a random person on the other side of the protocol, but we know that the conversation is not either eavesdropped.
Yes.
Right?
Yes, exactly.
So the next step is to establish who the person is, right?
Yes, you can, but how can you exclude that the identity will be not frauded? Will be not fraud.
No, you cannot. The first thing is always establishing connection. So until you actually exchange the keys, you have no confirmation that connection is.
There was also a second question, right? Or...
Michał, does it answer your question, or do you want to?
Yes, because I had the question with this low data rates. How long do we need to wait to establish like an eavesdropped connection before we can push more data? Because it looks like given the 0.034 bits per second or something like this, or even 3 per second, that's very low rate. Am I correct?
Yes, it's a very low rate, but we also have to remember that we are using this communication here to just create the key. So we are not using these key rates to push, to stream data. We are just using them to create the key. So once we will create the key, we can use, internet and that's it. So completely classical communications.
I understand. So if we had like half a kilobyte key,
yeah,
then possibly we could do it within a few minutes.
Yes. I think exactly minutes is the time scale at the moment. Yeah.
Thank you very much.
Okay, we have two other questions. Can we ask them now?
Yes.
Okay, so the next one is from Kevin. Kevin, can you also unmute yourself and ask?
Oh, it's mostly on that bullet point. Yeah, just curious about
it. Can you ask your question that you posted on the chat?
Oh, just curious about the third bullet point, the slide, current slide on the load at the benefits.
So sorry, I didn't get it. Sorry. Hello?
Actually,
maybe
yeah.
I will first maybe read the question on the chat. So Kevin asked, how does hybrid solution of BB84 and Aegis SIG reduces the QKD connectivity load from O(n) squared to linear?
Yeah, it is actually it is by the design of the network, because it allows in this experiment they have proposed to resign from the relay-based networks and to switch to all pass networks. In between the all the users in the network, there is a central authority that issues the certificate. Sorry, that was, where was this shown? I think it here. So that was this experiment that I'm talking about was actually designed to reinforce public key infrastructure. In this configuration, there was considered Trust Certification Center, which issues certificate for every user. This Trust Certification Center was generating the certificates exactly using PQC algorithms. So in this configuration, everyone who was joining the network had to receive a single certificate. In the usual situation, in the usual network, considered until now before this experiment, everyone who was joining the network had to exchange a pair of keys with everybody else in the network. That was the relay. Configuration. In this situation, everyone had to store about n squared pairs of pre-shared keys to be able to participate in communications in the network. Here, they have shown how to avoid that, and using PKI augmented by PQC, lowered down the number of authentication steps to n for n users. Does this answer the question?
Kevin?
Yeah, thank you.
Okay, good, thanks. There's one more question from Mohammad Reza. It's also quite general question regarding post-quantum algorithms. So Mohammad Reza, can you please unmute yourself and ask?
So sorry, I've got three questions.
Three questions.
I don't know
okay.
if you, I don't know if you have time. So. Can I ask?
Let's try.
So, okay. So the first one is, are all these PQC problems represented in a discretized format, for example, in a lattice structure? Because the two examples were like that. No.
No,
so,
it was. Mhm.
Okay. Sorry.
No, these were just two examples of one kind of PQC cryptography that is lattice-based. It's true that it's, I think, the most popular type of PQC, but there are many others, for example, code-based, isogeny-based. I am not an expert in that.
Yeah.
So
yeah.
I was not even going into depth of that, but it's a whole zoology of various kinds of problems, and I think there are at least six classes of PQC protocols. Just one of them is the lattice based. Yeah.
So the second one is, how can one be sure that there's no possibility to convert the problem to a form which is solvable via quantum algorithm using polynomial resources, polynomial time?
There is no certainty of this kind at all, and there will never be. Moreover, as I have shown initially, there is not even certainty that by classical means these algorithms cannot be broken one day. And for this reason, they can provide you only with the computational security. And I fully agree that this is a very very weak assumption, although seems that until now no one was able to demonstrate the contrary. But it absolutely does not mean that tomorrow someone smart will not be able to do that.
So, sorry, the third one is a general one. So generally when quantum effects accumulate, classical phenomena appear. Is there a smooth limit where this happens for communications or cryptography?
Sorry, I didn't understand you. It was
okay.
Can you repeat?
Okay, of course. So generally, when quantum effects accumulate, classical phenomena appear. Is there a smooth limit when this happens for communications or cryptography? And if yes, what determines a particular quantum cryptographic technique gets mapped to a classical technique?
Of course, yes. Of course, I mean, this limit of, for example, 100 kilometers for non-twin field-like protocols is exactly turning our quantum cryptography useless because our quantum resources are washed away. So yes, of course, there is a lot of problem with that. But some smart techniques such as smart protocol design and smart implementation, for example, using satellites, help us day by day, you know, extend these distances. What can I add? I mean, we definitely we will be never able to copy amplify quantum signals, so we have to develop some other ways. One possibility would be to construct quantum repeaters that will help distribute more efficiently to larger distances entanglement. People are thinking about this for already many years, but the problem seems to be quite difficult in its implementation. For example, some of its flavors require quantum memories, which are, of course, being developed, but not yet there. But I am hopeful that in some number of years we will have some quantum repeaters that will definitely help extending the reach. Mm-hmm.
Thank you. Thank you.
Mm-hmm.
Okay, I think we can proceed.
I think I am about to finish, so I just wanted to say that there is a lot of effort put into standardization. I have participated in the first standardization that was carried out by ITU. It took place in 2018. That was actually the initiative of the Hudson Institute in the US. This initiative has been followed by European standardization body, CENELEC. Now the standardization roadmap on quantum technologies is ready. And I think that they are already some standards are already European standards are already available. NIST is at the forefront of the standardization of post-quantum cryptography. They initiated this process in 2016 by opening the call for any quantum-resistant solution, primitives, including public key infrastructure, digital signature, and key exchange algorithms. The standardization process is supposed to finish with some recommendations by 2024. This is also process that is quite quite involving, because apparently the algorithms that were actually selected are not the strongest ones that were proposed. And among the finalists, there are, for example, Crystal Kyber 512, which offers lower security with what cryptographers wanted. And this raised a very vivid discussion and protest among mathematicians involved in this standardization. Nevertheless, NIST requests comments on drafts of 3 federal information processing standards, a module lattice-based key encapsulation mechanism standard, module lattice-based digital signature standard, and stateless hash-based digital signature standard. So these are all activities that are happening now. And with this, I would like to thank you very much for your attention. I would like to advertise our group. We are hiring now, so everyone who is interested in quantum communication is very welcome to talk to us. I would like to thank our sponsors as well. So Ministerstwo Edukacji i Nauki, NAWA, Narodowe Centrum Nauki, and European Commission. And with this, I thank you very much for your attention again.
Great. Thank you very much for this great talk. Thanks also for answering the questions that we've already had. Do we have more questions now? So we are just running out of time, but if there are some important, urgent questions, we can try to ask. I can see in the chat that there was one more question from Kevin. There was a question, can we see the maths proof slide for the long-range DI-QKD? And that was skipped. But then Adam Worachewski shared a link to the paper on arXiv, in which probably there's the math involved.
Yes, I think the question should be generally, does not have to generally apply to that protocol. It should, this question it would be useful to rephrase the question, what are the security proofs for DI protocols in general? It doesn't have to be this protocol. So DI protocols, these security proofs are based on entropy accumulation theorem, for example.
Okay, good.
And apply for collective attacks or collective attacks. So for all attacks that exclude the fact that eavesdropper can perform measurements, entangling measurements on all the copies of the qubits sent.
Okay. So earlier there was also a question about this 25% quantum bit error rate, but I know that it has been answered already during the talk. Is it clear for everyone, or someone like to repeat some parts? Okay, seems that it is clear. There was also one general question from Michał. So Michał, is your question still valid? Would you like to ask the question that you posted at the beginning?
I think I asked whether something would be discussed, and now I know it won't be discussed.
Okay.
But I do have open question. Will there be any, maybe in future, any lecture or presentation about parallelization and exponential speed up?
We can think about it. So there were some, let's say, introductory lectures in the past in which we covered some popular quantum algorithms for which we can just expect some speed up, maybe not necessarily exponential, but there was also a lecture about Grover's algorithm in which we have a quadratic speed up. I'm not sure. We can think about it. So if there is a good speaker,
if I say something, it's not about speed up. It's a reduction in the number of gates or steps of computation.
All right. Yeah. So anyway,
it would be great to hear about it.
Yeah.
Because
anyway,
I've been lecturing about it a lot, but I don't think we hear a lot about it. Nor do we hear if there is opportunity to use any quantum computing resources here.
So maybe just a general note. We are also looking for good speakers for the next episodes, for the next meetups. We have some candidates for the next 2 meetups in December and January. But if some of you would like to give a talk later in 2024, feel free to contact me. And if you have a good topic, we can try to organize a talk. All right. Do we have more questions to our speaker?
Sure.
Yes.
I'm a student from India to searching PhD position in quantum computing. If any professor listening to this talk, I can contact them, or I know this is unwanted information. So, yes, so that's it.
Okay. So if there are such requests, maybe please just contact me directly by email, and I can maybe I'll try to give some recommendations as well. But maybe if it was just a question to our speaker, whether there's an open PhD position, then maybe Professor Stawinska can answer. But
we are always in the search of talent. So if there is any application, we are happy to review.
Yes. So you can you can contact Magdalena directly. So there was a contact on the website that was shared, and yeah, so that's the best way, I believe.
Yes, sir. Thank you for your help.
And maybe for the end, I will also share a few slides. Okay, so this is the slide that I already presented, but yeah, I will also invite you to stay in touch, and also you can join our mailing list, our Facebook group, follow our Facebook fan page or YouTube channel. So as you can see, this meetup is recorded. So hopefully, if there are no technical issues, we'll try to upload the video to our YouTube channel, so it will be publicly available. So if you want to just stay up to date with the announcements, we invite you to just follow our profiles. And do we have some other questions? Maybe last chance to ask. Let's see the chat. Okay, I don't see more questions now. So with this, I would like to thank once again our great speaker for a very interesting talk. I believe that we've all learned a lot, and it was great. Thanks for answering all the questions. And I would also like to thank all the participants and for asking very good questions. So we hope to see you next time. So most likely the next meetup will be in December, but we are still organizing it, so there will be announcements within the next 2-3 weeks. So thanks. There are some messages. Yeah, so there are just some acknowledgements on the chat, so I can see that all the participants like this talk very much, which is great. So we are all very happy. I will now stop recording and also stop sharing the slides.